Daniel, please take us away. Thank you.
Gracias Nidia por la introducción, gracias ahí por la invitación. Y bueno, contento de estar acá y
Thank you so
ayudándolos
much
a
for
organizar
introduction.
todo este evento y esta versión del Kiss Kit Fall Festival de este año. Vamos
And
a
I'm very
empezar.
happy to be here at this event, Kiss Kid Fall event.
Bien, primero que nada,
Let's
pues me
start.
presento a QNow y nuestra misión. Somos una compañía de minería y generación de conocimiento donde ayudamos a las empresas y científicos a acelerar
We're a
el
company of
descubrimiento
mining
y
and
eficacia
generate
de las conexiones entre los datos
knowledge.
para la
We
automatización de
help
procesos,
companies and
aplicaciones y
scientists to
insights
accelerate development of
que
applications
faciliten
and new connections of
para
data
que agreguen valor
for the
y
automation of processes, procedures,
a
and
la
generation of
organización.
insights
En
and
QNow
anything else that can
somos,
add value.
somos cuatro founders. Está Alejandro Giraldo, nuestro
Within
CTO
AI
Alex,
into the
nuestro
business,
CRO
the investigation,
Nicolás
we
Lugo,
are four founders,
nuestro
Alejandro
CFO.
Giraldo, our website,
Bien, hoy tenemos agendado y vamos
our
a hablar un
site is
poquito
Mariano Caruso, our
de
CEO is Nicolás
lo
Lugo.
que respecta a uno de los algoritmos que son bastante importantes. Justamente se compone tanto de la parte clásica como de la parte cuántica. Es el Variational Quantum Eigensolver. Así que, bueno, vamos a ver una mirada detallada de qué es, cómo funciona, cómo se puede implementar y para qué nos sirve a nosotros este tipo de algoritmos. Para hoy, entonces, como mencionó Nidia, eh, tenemos agendada la parte uno, ¿sí? La parte uno va a ser los fundamentos de este algoritmo. Y para la parte 2 que sería dentro de 8 días, sería la parte ya más de Quantum Chemistry, donde se implementan estos conceptos y estas funciones ya propiamente creadas de antemano por el framework de Qiskit para el approach en la creación de nuevos materiales, para la creación de nuevos fármacos y demás cosas. Empecemos entonces. ¿Qué es el Variational Quantum Eigensolver? Como mencionaba anteriormente, es un algoritmo que está compuesto de un lado cuántico y un lado clásico, ¿sí? Em, este algoritmo se compone o tiene cuatro componentes que son bastante claves para la conformación y los resultados de tanto el input y los outputs. Para entender un poco más el tema del input o qué clase de input
To understand the input and outputs
usamos en
for
este caso,
a little bit better,
recomiendo ver
what the
la
type of
sesión que
the
tuve
topic of input
con
and the type of
nosotros
input.
en la parte de data encoding, donde pues muestra un
We
poco
use a type
cómo
of algorithm
funciona
recommended
de
to
qué manera
see the
se
session.
pueden embeber datos en sistemas cuánticos, ¿no? Puntualmente asumiendo que conocemos ya esa parte, volvemos acá donde mencionaba el Variational Quantum Eigensolver tiene cuatro componentes, ¿sí? Se compone de un operador que puede ser la descripción de nuestro sistema a nivel de energías, lo que formalmente llamamos un hamiltoniano en español. Se compone también de la parte del ansatz, que formalmente es nuestro circuito, la conformación de nuestro
Okay, the
circuito.
VQE
Y
is
también
composed by the operator, the ansatz, and the estimator,
un
and a
poco
classical
un
optimizer.
optimizador de qué
This is
hacemos.
formally our circuit,
Esta parte es la
the
que
way that we
conforma
compose the
digamos
circuit,
que este algoritmo híbrido, ¿sí? Del
and
cual
this
estamos hablando.
algorithm,
Puntualmente,
hybrid
el algoritmo, como
algorithm, that's
mencionó
from
Julián,
some way, from some
lo
manner,
describimos como un hamiltoniano o un modelo matemático que
and we describe it
representa
as a Hamiltonian
toda la energía
or
de nuestro
a
sistema,
mathematical
¿sí? Para nosotros
model.
poder embeber em, nuestros datos o embeber moléculas, inclusive en términos cuánticos, se tiene que pasar por un proceso en el cual pues una computadora cuántica lo entienda pues de manera correcta, ¿no?
Okay, the way that we have to do it
Matemática
is that we
es
need
una
to
computadora
make the
cuántica
information put together so the quantical computer
trasladando
or com
el problema,
can
transformándolo al
understand it.
sistema en términos de operadores cuánticos, ¿sí? En este caso puntualmente estamos viendo operadores basados en compuertas universales, ¿sí? ¿Cuál es el objetivo como tal de un Variational Quantum Eigensolver? Bueno, encontrar en ese sistema, ¿sí? ¿Cuál es el mínimo de energía en términos matemáticos se representaría en el mínimo eigenvalue como tal del sistema, ¿sí? Eh, o cuál sería ese ground state de este sistema. Este es el primer componente para entender un poco
From
este
this
algoritmo.
system, that is the first component to
Por otro
understand
lado,
a
¿qué
little.
sería ese eigenvector en
And the
sí?
algorithm, on the other hand,
Hagamos de cuenta
that
que
would be the
tenemos la
vector.
matriz de una matriz de datos que
In
represente
mathematical
el
terms,
hamiltoniano, ¿sí? Que represente este tipo de sistemas.
let's
Y este
pretend that we have the
componente
matrix of the data matrix
el
representing the
eigenvalue
Hamiltonian,
sería ese
which
valor o ese
represents
ground
these kinds
state
of
mínimo
systems. And
en el
basically,
sistema,
the
¿sí?
aging
Así como se
value.
hace de
Would
manera
that be the value
estándar.
of
Ahora vamos
or
a
the
ver
growth
en
of
detalle
estimate
en el
minimum
código
in the
cómo
system?
se haría esta parte. Mi perfil va más hacia el lado técnico, el lado de software, ese es mi background. Así que si tienen alguna duda un poco más formal con respecto al modelo matemático o a la parte química, nos la pueden dejar directamente
If you have any
en
questions
el
about the
chat y
mathematical
ahí
formula to the chemical part,
la
you
pueden
can leave it directly on our
responder.
chat, on our disk,
Em,
and one of our
por otro
organizers
lado, y
can help
segundo
you with that.
componente que tenemos a nivel de este
On the other
algoritmo
hand, the second
es la
component that we
parte de
have at the level
ansatz
of this
o
algorithm,
popularmente reconocido este término de una palabra pues alemana, ¿sí? Traducido al inglés quiere decir el approach y potencialmente traducido al español debe decir el enfoque, ¿sí? Digámoslo de esa manera.
okay,
¿Qué representa este componente de ansatz en un algoritmo
translating the term, sorry, this component of
difícil?
ansatz is an
Representa
algorithm and
justamente
several
la cantidad de compuertas, la cantidad de qubits en términos de qubits precisamente que se utilizarían para poder procesar y poder generar nuestro output y poder
the
hallar
ambiguous, I mean, the ambiguous
un
represents
nodo
exactly that, the number of sluice
ground
gates, the
state, que
number
es
of
el mínimo
qubits.
valor de energía
In
que
terms of
existe
qubits,
para un
precisely that they
sistema.
would be used for power,
Entonces,
process, and be able to
es clase
generate our
ansatz
output and
y
being able
antes
to
de
find
esto
that.
dependerá del performance
Ground state with
de
minimal energy value
la
from a
cantidad de
Hamiltonian of a
compuertas
system.
que utilicemos, la cantidad de
So
qubits que se usen al momento de ejecutar y resolver un problema de este tipo.
this will depend on the
Así
performance of the
que
results, the number
es
of gates we
importante
use, the number of qubits that are
definir
used when
de
executing and
forma
solving a
apropiada
problem of this type. So
qué
it is
tipo
important to
de,
define well
de esquemas
and or
para
the
el
most
procesamiento de
appropriate
este tipo de
manner
algoritmos.
this kind of algorithms.
Por otro lado, y como tercer componente,
On
tenemos
the
la
other
parte
side,
de
and the third component, we
estimaciones,
have the estimator,
directamente
estimations.
las medidas de justamente la parte cuántica de este algoritmo, ¿sí?
This will be the
Eh,
measurements for the quantical section or component of
una
this
vez
algorithm.
que nosotros hemos declarado ya y formalizado nuestro hamiltoniano conocido o no conocido, ¿sí?
And
Ya
once we
hemos
have set
definido
up our
nuestro ansatz,
Hamiltonian known or unknown,
que incluso Qiskit ya tiene ansatz predefinidos, ¿sí? Y una vez
we have already defined our tenants
hemos medido
here.
ya el sistema, bueno, pasamos a justamente a este componente donde podemos determinar eh, el tipo de output a nivel clásico y este tipo de
We can
output
move to the to this component. We
poderlo
can go ahead and determine the output
ejecutar
of
o
this classical
poderlo
level,
post procesar de alguna forma
and this
de
will allow
manera
us to
clásica,
process
¿sí?
for
Para esto,
some
este
manner.
estimador va muy directamente correlacionado al siguiente componente que es nuestro optimizador.
For this, the estimator, it will go
Generalmente
directly correlated to the
se
next
utiliza
component,
un
which is the
reference de
optimizer
aquí la parte
or
clásica y
optimizer, like the
hay
classical optimizer.
diferentes tipos ya conocidos, muy conocidos, como es un
We can use
optimizador
different
A
types
que
of that are very well
se
known,
recibe en redes neuronales, o los más clásicos y más usados como el Covila, el
or the
SLS4
more known optimizer
y
to
demás
the
optimizers,
Kobe,
inclusive
DSL.
basados en gradiente descendente, que busquen o que sean esa función clásica que nos den como resultado esa función de costo directamente, ¿no? Que sea esa descripción formal de la función de costo.
And this will not direct, will be cost
O
related.
estar
It will give us a
directamente en
formal
código,
description
así
of
poniéndole un
the
poco
cost
más
function.
claridad
Let's look at the code
de qué
directly
estamos hablando, ¿sí? Para que
so we
ustedes
can understand
entiendan
what we're talking about.
cómo planteamos estos problemas en términos de código, cómo los
How do we
ejecutamos
plant this in a setup of a code?
Em, recuerde que esto está basado directamente en el contenido de IBM. eh,
This is directly
el notebook
aligned with the
y
IBM
los slides
content.
los vamos a compartir
The
Daniel,
notebook
directamente.
and the slides, we're going to share
¿puedes
them.
expander con el mouse para que se vean las letras un poquito más grandes?
Sí, sí, por supuesto.
We're
Perfecto.
making the screen a little bit bigger
Gracias.
so you can see it better.
Directamente este contenido está apuntado para que em,
This
nos
content
podamos
is
por lo
targeted,
menos ganar el batch de este tipo de algoritmos, ¿sí? Así que nada, también si surge alguna duda con respecto al código y demás, nosotros la podemos ir atacando directamente em, asincrónica desde el Discord. Bueno, de vuelta, acá vamos a ver, vamos a darle a ejecutar todo. Como mencionaba, este código está basado en el contenido original de IBM. Obviamente que tiene
this is
alguna que otra
correlated to the IBM
modificación
content, original
que
content.
ahora puntualmente las vamos a ir viendo, ¿sí?
Now we're
Pero
going
en
to
la primera
see
parte
it
vamos a hacer
directly,
toda la
step by
instalación
step,
de librerías, ¿sí? Necesarias para correr un BQE básico, funcional, ¿sí? Por
and
otro
they will
lado,
be all the library
estos
installation
canales
needed to
van a tener
run.
centralizados los conceptos que recién vimos en los slides, ¿sí?
And this will allow
Vamos a
us to
ver
see the
qué
concepts that we
manera y a
just
nivel
saw
de
in the
código
slides.
nosotros podemos representar un hamiltoniano, ¿sí?
How can we
Un
represent
hamiltoniano
a
que vendría a ser
Hamiltonian?
a nivel de código. Básicamente
So we
podemos
can see it at the
decir que
level of
representa
a
una
coding
especie
level.
de matriz, es la representación de, de los
We can say that
de la
they
teoría
represent the
que
kind
hay
of
en el sistema,
matrix.
¿sí? Se puede ver representada en
Here you can see
diferentes
the loss of energy
formas.
from a
Podemos generar
system.
hamiltonianos de diferentes maneras.
You can see
Inclusive
it
ese hamiltoniano
representing the
queda
Hamiltonians in different
serializado.
manners.
Para el enfoque químico, seguro lo vamos a ver en detalle en la sesión que viene, pero para que
For the
tengamos una
chemical
idea,
approach that we're
un
going to see
hamiltoniano
directly in the following
vendría a
session.
ser la representación desde el nivel electrónico de una molécula, ¿sí?
This will be the direct
Cómo
representation
está
from
el
molecular
electrón
level.
puntualmente, valga la redundancia, está modelado de alguna manera, está mapeado en ese sistema, ¿no?
And this is mapped in that
Sistema
system.
que cuando hablamos en términos de química o aplicaciones de química,
Whenever we talk
vamos a
about
tener
chemistry
las
and applications
aplicaciones
of
que están
chemistry,
modelando una molécula, inclusive hasta con los electrones, ¿no? Hasta ese detalle
we're modeling a
nos
molecule,
permite
even
representar un
electrons,
hamiltoniano, ¿sí? A nivel de código, como les mencionaba, se representa de esta manera, ¿sí?
in the way of a code level. This is the way that is
A nivel
represented.
ya y pasando por cada uno de los componentes desde nuestro ansatz hasta nuestro optimizador clásico, podemos
And
ver
seeing all
que,
the components
como lo
from our
mencioné recién,
anchor, our classical optimizer, we can see
está
that.
detallado la parte pues, matemática, ¿sí? La parte fundamental, y a su vez vamos a ver ya directamente de qué manera es que se ve a nivel de código, ¿sí? Una vez que ya tenemos un hamiltoniano, ¿sí? Que obviamente hay que procesarlo de manera adecuada, ¿sí? Ya que pues no todos los hamiltonianos eh, son iguales, no todos los hamiltonianos van a dar el mismo resultado, ¿sí? Inclusive mezclando técnicas con diferentes optimizadores, ¿sí?
Not all the Hamiltonians are the
Vamos a ver
same,
aquí.
even though you're mixing
Bueno, ahora volvemos directamente a la
certain
parte
techniques with different
de cuáles son
optimizers.
las ventajas con respecto a cómo se hace actualmente de manera clásica este tipo de approaches de buscar el ground state, ¿sí? Pero bueno, volviendo aquí al código, digamos que ya tenemos un hamiltoniano declarado, ¿sí? Eh, Nosotros a nivel matemático y buscando de manera clásica ese mínimo eigenvalue, ¿sí? Lo podemos hacer directamente solo con una línea de código, directamente utilizando funciones de NumPy, ¿sí? De linear álgebra, ¿sí? Una vez que nosotros ya tenemos nuestro hamiltoniano, que es el primer componente,
Once we have the first
tenemos
component,
que
which is Hamiltonian,
transpolar este hamiltoniano, esta descripción del sistema, ¿sí? En términos
and we have to
cuánticos,
transpose this
de una manera
Hamiltonian, the
básica como
description of
a
the
través de
system,
un ansatz.
in
Y
quantum
como
terms.
mencionaba, ya hay ansatz que están predefinidos, ya están
You will see that there are assets already
ejecutados, ya se hacen
predefined.
inclusive benchmarking con diferentes casos de uso directamente en Qiskit y simplemente llamando
The three videos just
desde la
tested already
librería
have been
simplemente
benchmarked with different
podemos
use
hacer uso
cases
de estas implementaciones, ¿sí? Una vez que
directly in
nuestro
Qiskit.
hamiltoniano ha sido
Once our
traducido en
Hamiltonian
términos de operadores cuánticos, pues lo podemos ver
has
de
been
esta manera,
translated into quantum operators,
donde directamente pues vamos a tener eh, qué cantidad de compuertas y qué cantidad de qubits estamos usando, ¿no?
we're
Una
going to
vez
see what kind of
tenemos
keywords we're
ya
using
nuestro hamiltoniano en términos cuánticos,
in quantum
lo que
terms.
resta es pasar directamente nuestro ansatz y nuestro hamiltoniano a ser medido directamente en el sistema. En este notebook lo podemos hacer de dos maneras. Obviamente que aquí está el approach en un simulador local, ¿sí? Pero también cambiando este flag y ustedes configurando individualmente ya su token de Qiskit y del IBM Cloud, lo podrían hacer directo en un hardware real, ¿sí? En este caso lo vamos a hacer en un simulador, ¿sí?
We're going
Eh,
to do it in a
y
simulator,
como resultado,
and as a result,
nuestro sistema en términos cuánticos,
within quantical
vamos a ver que
terms,
cada compuerta que vimos aquí también se puede ver representado ya en compuertas directamente universales, ¿sí? No tan
we will see
primitivas.
that in each gate.
Eh, Cuestión de que una vez ya tengamos y sepamos cuántos qubits vamos a usar, cuál va a ser el deep o la profundidad de nuestro circuito, cuántas compuertas vamos a tener que implementar y demás, podemos inclusive llegar a determinar un tiempo aproximado, ¿sí? Para esa
We can even
ejecución.
determine approximately
Puntualmente,
time.
si este mismo hamiltoniano que vimos arriba de 16 por 16, ¿sí?
This Hamiltonian that we see above
Funciona en
16 by
una GPU
16,
real, probablemente se
it
nos
runs
tome
on
ese
a real
tiempo
PQ
implementarlo,
processor.
pero bueno, como lo estamos ejecutando en un simulador, vamos a ver directamente que la configuración es la siguiente. Tenemos por defecto 10.000 shots, 10.000 pasadas por nuestro algoritmo, ¿sí? Nuestro estimador pues es un simulador que,
Our
directamente.
estimator, as it happens, is a simulator.
Esto es para más adelante plotear los resultados y llevar trazabilidad, ¿sí? Las iteraciones máximas que tendríamos a partir pues, de implementar el algoritmo, ¿sí? Vamos a ver que de todos estos valores, de todos
We will see
estos
that out of all the values
resultados que nos estaría dando ya directamente nuestro optimizador clásico,
that it
el
will be
que
given to us
más
by our classical
considera
optimizer,
es justamente el mínimo de todos esos valores, ¿sí?
the minimum
Si
for
ese
all of those
mínimo va a ayudar a
values,
determinar diferentes
will help us
outcomes
determine
o diferentes approaches, ya
different
sea para el
approaches.
enfoque que queramos llevarlo desde, como mencionaba al principio, el desarrollo de fármacos, eh,
For instance, if we want to
especialmente
develop
la creación de un modelo,
pharmaceuticals,
¿sí?
like we mentioned at the
Entonces,
beginning,
todo este proceso va a ser realmente
or to simply create
predefinido de
material,
lo que vendría después. ¿sí?
This whole process is going to be
Una vez ya
the input of what we
tengo
call
el sistema
NIPS.
corrido ya las ejecuciones y demás, vamos a poder ver ya en términos generales y a nivel visual, bueno, cómo se comportó
Once the system is running, the
toda
executions were
esta
and are
ejecución
done,
desde
we're going to
por ejemplo,
see in general
con
terms
nuestro
and a visual
EnLuz,
level
desde
how
el
this will
performance,
perform.
desde nuestro optimizador y directamente pues desde
All
nuestro
this performance
optimizador
from a once
a
unknown
resultados
or
como
known
último
Hamilton.
con respecto al tiempo y respecto a las iteraciones que hemos hecho. Em, de esta manera es como llegamos ya a resultados que nos pueden
This
dar
is the way that we
argumentos
get reach results
y terminar de evaluar o llegar a conclusiones
and stop evaluating or reach
hacer
conclusions.
o llevar hacia de cara al negocio, ¿sí? Directamente si es un tipo de exploración interna en alguna empresa, ¿sí?
If it's an internal exploration within a
Las
company.
características buenas y las desventajas, ventajas y desventajas de nuestro algoritmo,
Advantages and disadvantages,
bueno, que justamente eh, como fortalezas o como cosas buenas,
the strengths,
es fácil de alguna u otra forma la implementación, ¿sí?
the implementation,
Em, el uso de este tipo de algoritmos a
the
nivel
use of this
teórico,
type of algorithms.
tanto en la parte teórica, ¿sí? Como en la parte fundamental, matemática y demás, em, tiene ya todas las, digamos, validaciones
Has all the
teóricas
validations,
y aplicaciones y resultados a nivel teórico que obviamente
and the
determinan
applications and
de alguna u
validations
otra forma
theoretically,
que a través de un buen planteo de un hamiltoniano, un buen planteo de un ansatz,
that once a
¿sí?
well
Podemos
a
llegar
thorough approach
a
of the
optimizar
Hamiltonian or a
correctamente,
huge approach
¿sí? Este
approach of
tema
this
de
answers from the
si se
optimizer,
corrió este algoritmo
we can even reach a
beneficioso
quantum advantage.
directamente por ese detalle, ¿no? Toda la teoría lo avala por detrás,
All the theory will support
justamente
it.
con esta intención, ¿no? De que a través de este tipo de algoritmos podemos generar ventaja cuántica. ¿Por qué? Porque
Through
de
this type of
manera
algorithms, we're going to be able
de manera
to
clásica, como se hace hoy en día,
develop
los
quantum
algoritmos se ven
advantage or
limitados
generate
y
quantum.
justamente y a nivel teórico se resalta que este tipo de algoritmos rompe esas barreras, ¿sí? Entonces es importante analizarlo bien a detalle, analizar bien
It
los
is very
resultados,
important to
¿sí?
analyze in detail and analyze
De
it
qué manera
well,
ejecutamos
the
este
results
tipo de
in
algoritmos
which we
y si
execute
ya
the
lo llevamos
information.
y lo traspolamos a un QPU real a nivel de
And the
código,
way that we transport it to a
pues
QPU, a real QPU,
todavía no es tan ventajoso, ¿sí? Pero desde el punto de vista del uso de qubits, desde el punto de vista de precisión e incluso speed up, podemos decir que es donde nace pues, la ventaja de este tipo de algoritmos, ¿sí?
and this is where
Em,
the advantage of this type of algorithms
otra
goes.
ventaja, podríamos decir, otra fortaleza de este algoritmo es que podemos inclusive generar o hacer ejecuciones simulando inclusive modelos con ruido, ¿sí? Podemos directamente crear dentro de nuestro ansatz o implementar modelos que se asemejen lo más parecido a la ejecución en un
We
hardware,
can find models that
¿sí?
transform
Y
themselves to
una de las desventajas, ¿sí? Y como
to the real scenario.
es
And some of the
poder
disadvantages,
tener o que la relación de un hamiltoniano de un uno a uno en el uso de qubits, pues no es tan performante. Por eso directamente al nivel de traducir de alguna u otra forma este tipo de hamiltonianos, lo vamos a ver bien en detalle en la parte química. No traducimos directamente todas las
we don't translate
características,
directly the
digamos,
information or
del hamiltoniano, sino que
the
traducimos
Hamiltonians.
partes del hamiltoniano de manera pues que sea más óptima el
Instead of
cálculo
our Hamiltonian, we are
de
taking the
los
parts
efectos
of it. In this way, we will be more
de las
optimal and the
desventajas.
calculation.
Después, bueno, ya a nivel más de detalle, vamos a poder verlo en las
um,
referencias citadas en el notebook.
and the calculation, and this is one of the
Otro detalle
disadvantages.
antes de que se me
Next will
pase
be at a more detailed level, we'll be able to
es
see in the references cited in the notebook.
tiene que ver con el tema
One
de la
more detail
comparación de
before I
los
move
sistemas
forward
previstos, tanto
is
clásicos
that
como no clásicos, ¿sí? Bueno,
subject
hasta
of
qué
various
perspectiva
methods,
se
both classical and non-classical.
a qué desde qué speed up o qué nivel de speed up maneja este algoritmo, ¿sí? De qué manera escala. Y aquí es donde, reitero, es donde está la ventaja de este algoritmo, donde nos puede llevar a una ventaja cuántica este algoritmo usado pues de manera correcta, ¿sí? Em,
The way of the scales on this here, I
Recuerden
reiterate, this is an
que si
advantage
algo
of
sabemos
the
para
algorithm
representar
lines,
las
where it can lead
funciones
us to a quantum
de nuestro
advantage.
nivel mínimo
This
de
algorithm, once used
representación
correctly, from the
y
moment you
digamos
initialize the
de forma
parameters to
argumental
certain
comparada
functions
con el método
within our
clásico,
minimum level of
¿sí?
energy, our ground states,
Em,
there is some advantage compared to the
este
classical
sería el
model.
proceso por el cual se hace de
This
manera
is the
correcta
correct
y
process,
este sería pues una representación del proceso de manera clásica, ¿sí?
and the other one is a
Obviamente
representation
tenemos
of a
que
classical model.
tener de alguna u otra manera un valor inicial para empezar a generar nuestra función de costo
Here you have to
comparado
have
con lo que mencionaba con respecto al proceso cuántico,
initial value to create a
nosotros vamos a
cost.
tener esa evolución del sistema de alguna otra forma pues cubierta, ya que se haría
Here we're going
de
to have the
manera
evolution of the system in some other form as covered,
en
and it
serie,
will be in a different way.
¿sí? Pero bueno, a nivel general,
In general
estos son los
context,
conceptos básicos, estos son
these are the general
la manera
concepts.
en que funciona este tipo de algoritmo. Em, Puntualmente, nuestro enfoque acá es mostrar la funcionalidad de este algoritmo en la parte química, ¿sí? Mostrando el valor agregado que da em, en esta industria, en estos casos de uso. Em, Así que, bueno, espero que se hayan podido llevar algún entendimiento, se hayan podido llevar la
I hope
representación
that you
desde
had
un
some
inicio
understanding
numérico eh, hasta la representación formal en términos matemáticos de qué es este
until the
algoritmo,
representation of
¿sí?
mathematical terms.
Cualquier duda o cualquier pregunta que tengan,
Any
la
questions or
pueden
any
hacer
concerns that you
directamente
have,
desde el chat o por el Discord, sin problema.
you can put it
Muchas
within the chat,
gracias.
or we can do it within the Discord without any problem. Thank you.
A ti, Daniel, excelente presentación.
Thank
Realmente
you, Daniel.
muy
Excellent
claramente explicado.
presentation.
Y
Very
me
clearly
gustaría,
explained.
sorry, excellent presentation, Danielle, and very clearly explained and complemented with theory and code. I would like to open it to questions now. Please feel free to ask questions in our live questions section, where if we don't get to them now, we can answer them later, or right here if you would like to go directly on the chat. Just give everyone a moment.
No, gracias por el espacio y bueno, recomendado un poco para entender de vuelta la presentación de su weekend del día lunes, que sería de gran ayuda para entender un poco la parte pues, de cómo representamos datos y de qué manera en términos cuánticos podemos procesarlos directamente en un QPU real, ¿no? De manera correcta y eficiente.
Exactamente. Okay, it doesn't
Thank you.
seem
Thank
like
you.
we have any questions right now. So what I'm gonna do, Ali or Fabian, can you check the Discord 1 second? I just wanna make sure that we have this. Okay. All right. Now, I'm going to ask Nancy to shift to Spanish, or I'm going to be presenting well, actually, I don't know if that's going to work.
Cambiar a
No
español.
sé, Daniel, si me podrías ayudar a traducir lo mío a español.
Por supuesto, hay
Ok.
cambio de mi idioma.
Entonces, tu idioma sigue en español. Tú te quedas en
Ok,
español. Ok. Y porque la vez pasada no funcionó cuando lo hicimos. Last time it didn't work when we did the shift right in between. So I think that what we're gonna do is, Danielle, I'm gonna stop Nancy's interpretation, and then I'm gonna make you an interpreter now, Danielle, since your language is already set. And okay, so I'm going to put Danielle here. And so I'm going to be using which one? Daniel Ruiz video for the audio, right? Okay. So you're gonna go from English to Spanish. I'm gonna start that. Let's see how this goes. Okay, can you say something, Danielle? Yeah. Okay. So we are good here, and I'm just gonna let me close this out and share my screen. Boop, 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 boop. Okay, you should see, just let me know if you can see my screen with a thumbs up. Thumbs up? Yes? Okay. Very well. So let's get started here. We just heard from Daniel Ruiz from QNOW Quantum Chemistry. I am going to, you heard the simultaneous translation into English by Nancy Reeves, and I'm going to have the fun task of presenting to you quantum teleportation and basis of quantum cryptography. Before I go into a lot of the detail, what I would like you to think about is this is usually presented with an example of Alice and Bob, but I'm going to try to present it in a little bit of a sillier way so you can grasp the concept, and then I will show you where it is explained in a technical manner with the size state and the different combinations. So some of the critical things that you should know here is that we're going to talk about gossip, chisme. And so I'd like you to think about quantum teleportation as the basis of cryptography, meaning even if we have a quote unquote bad actor, we're just going to pick on El Zorro, whose name has been intentional because the Z represents the Z plane in which the negative phase needs to, is what keeps this quantum information, so to speak. And we are going to be looking at both classical and quantum registers. Earlier, we spoke about what was needed for us to be able to entangle two qubits. And I'm just going to move this chat over here in case there's any kind of problem with no. Okay. So what we're going to do is we're going to look at this process from Alice and Bob, and let's take a deep dive into this. So our quantum gossip crew, or little chisme crew over here, is a messenger, which is represented through an astronaut because entanglement can happen at very long distances. As you know, KQD is satellite communication, and Alice is the keeper of the gossip, and Bob is going to be the receiver of it. And the acronyms here of the negative zero is, so when you look at the math, you can remember negative Z plane and what that means so we can recover the information, okay? Now, their roles are, as we said, the transport of the information. The astronaut really is going to carry the instructions. So what I want you to think about is like, okay, well, if this is super secure communication, we have in reality two individuals involved with a quantum and a classical circuit. This is, you know, the listeners, right? People observing. The information that is sent is an instruction. And so it's important for us to know this. This is what the protocol looks like. And so the qubits here would be A and Q. And the gates that we kind of looked over before, and this is a CNOT gate. This is a Hadamard gate. If you remember, the Hadamard gate is a particular, it's explained many times like a split of light. And particularly what it does, and the second portion is 1 over 2 to the square of the second state, which means that there's a sort of equal probability, right? We're not looking at additional experts here, but what's very interesting about this that I always enjoyed was the classical registers here that that also are involved in the transport of this information. So the information that that Alice and Bob share is going to be a set of steps and an entangled step. So before we get into this, and this is a measurement for those that are not familiar, and this is the X gate and the Z gate that needs to be applied to retrieve that information. So what's she talking about? Let's go into this a little bit more. So the entanglement connection here is takes place at long distances, and we like to think about this as something that involves a phase change, both for the encryption and decryption of the information. Remember, in all of this, it's how are we sending, how are we receiving, and what kind of information do we need in order to be able to get that message without giving away our codes. Even in the current encryption models, we always have problems described as NP hard mathematically, and the point is that there is always a portion of the information that is known and a portion that is not known, and that is a portion that would be received that would be within the recipient to be able to decode that information. And so here's a representation of the CNOT and the Hadamard gate. And the mix of these is going to be able to send it through the cosmos. The astronaut here in this analogy, what they represent is the classical bits that are sent. And we want to, you know, whichever the message is, the set of instructions to be able to decrypt it is what is going to be very critical for Bob to be able to rebuild that gossip. And so what does this decoding of the secret look like? It is the application of those instructions in the second part that is going to be critical for him to get the message. Now, in terms of this this information transmission, it's actually teleported, right? The astronaut's just an analogy for you to remember long distances. And it's important to also note that the moment that she sends the information, she cannot be able to share it with a third party because it vanishes. So even if someone was listening, they would need all that entangled qubit, the instructions, and because the moment she looks at those instructions, it collapses. There is no way that that our little bad actor hero Zorro, with a negative intention, can reconstruct that message. Now, many people have different myths about quantum teleportation. What's really critical for you to understand is that it is a basic set of protocol to transmit information, not particles. And in it, we involve both classical registers and quantum registers, meaning in a way it's hybrid technology. And it is a communication framework, meaning that there's going to be steps of recipient, there's several actors that are needed, and there is no eavesdropping available because of the nature of the information that once it is observed, we cannot reproduce it. Now, what does this circuit look like? If you look over here, C represents this classical register. And we have these are different examples within the IBM suite of information. What we see here are different points of time where there are measurements. And this is a unitary matrix that, for example purposes, is used at the end to make sure that the hardware itself is recreating that state properly. But it's mostly for informational purposes only. So when you look at this over here, we have two measurements that take place, and there is a flip of a dependent qubit, right? So this CNOT means that the state of one is going to immediately change the state of the other. Meaning if Alice sees a 1, Bob is immediately going to get a 0. If Bob, and vice versa, right? If she sees a 0, then this CNOT is going to flip, which is it's a NOR, right? This is like an X gate with a and the code I'll show you in a second. And so it is really important for you to know that these decoding instructions here are what allow us to receive our classical register with the information. So this is a different representation over here on the probabilities. Just remember, no matter what, this is a coefficient, right, of this ket, and the sum of the square root of these is always going to be 1. So no matter what the probability, whether it's 50-50, 75-25, of what we can observe when Danielle was explaining the shots, right? We're going to look at it to see what the probability of this is going to be in, 10,000 shots, 10,000 observations, then we would always know that the sum of them is 1. And when I understood that, despite the entanglement and the observation of the qubit, what keeps the state in almost like a teleportation way is the Z phase, because when we observe the CNOT, mostly with these two qubits, is going to be determining whether it's 0 or 1, and then the other one is just keeping it in the Z plane, sorry. So in the explanation that we're going to look at, you're going to look at these different states, point of time of measurement. And I want you to remember from Renel's presentation from IBM that we had, in order to have entanglement, we needed to have the possibilities where it would be either 0 and 1 or 1 and 0, or as you grew with the qubits, right? Not every combination of states was going to be an entangled states. So the steps that we follow in order to reach that is also going to be represented within our information here. So actually, I'm going to stop sharing this and show you the what it looks like in the IBM in the IBM explanation. So there is a notebook that you can download. And again, our objective here is to help you achieve the certifications. So let me just open this up quickly. Okay. All right. So I'm going to take you back over here on these courses to remind you, what is it that this group of individuals is trying to help you achieve? Now, there is two places that you can make, two ways that you can make it here. You can look at all the courses, or and you can look at the basics or the fundamentals. The notebook that we are going to be sharing and reviewing with some cheat sheet videos has to do with the fundamentals of quantum algorithms. I'm going to cover a little bit of some of the bases. Now, what we're doing with the quantum machine learning track is helping prepare you to, pass and achieve this badge. And with what Danielle was explaining, right? This quantum chemistry with VQE, and what do you need to know? What is understanding? Last year we had done, variation algorithm design, and we want you also to be curious about this quantum computing for business. So quantum safe cryptography, if there is an additional interest, we can provide you support in also achieving these badges. Now, let me go back here into where we were. So we're here in the basics of quantum information, and we're looking at what they describe as quantum teleportation. Now, we're talking about Alice and Bob here with the state, and that we're trying to, that we're starting with. And then we want to make sure that we have this third qubit that's going to be sent to Bob, right? Which you could think of the envelope, and it is considered to be unknown to both Alice and Bob until it is measured. And what's critical here is for you to understand that we don't know the state of a qubit until it is observed, which is why we talk about probabilities in our simulators. When you come down here, it talks about the entanglement necessary and different things. And I'm just going to walk you through the math a little bit. And here's what we talked about, the protocol, right? So you see this bit over here that's unknown. The measurement that Alice takes will flip this state. If this is a 0, this will be a 1. Hadamard would do what it does. And then when he measures it with the Z gate, boom, he brings out what was hidden in that phase. Now, for her, when Bob does it here, first he has to apply the reversal of it. So follow me for a second. If this is a 1, and this is a 0 here, sorry for that 0, they apply the Hadamard gate and then the Z flip. We're talking about the states of this C naught does not operate on a Z plane, right? It operates on the qubits itself. Now here, if Alice says 0, this flips to if Alice says it's a 1 and this flips to a 0, for Bob to be able to read the information, we have to undo it, right? Do this reversal here, and then flip the C naught. And so then we would apply, if she's a 1, we're going to flip it to a 0, and then he can get the, and then he'll get the second portion of here, which is the Z gate. And then that will be in all 3 planes of our block sphere over here. And so this would be the Z gate that holds this, and then the Hadamard is going to be on the other one. So again, it really depends on when we are looking at it and how we are looking at it. So let's take an exploration down through the math. The intent of telling you that we flip it is so you know that when we do the math here, why there are some combinations here. So if alpha is 1, then Bob performs a bit flip or X gate to his qubit B. If B is a 1, then he will perform a flip or Z gate on his qubit B. Now, if this condition for the 2 qubit system 0, 0, 0, 1, 1, 0, 1, 1 performs the operation, the identity matrix, that the unitary, right, matrix that we saw on this qubit for the Z and the X. So this would help us say that the protocol would effectively be implemented for a perfect qubit communication channel, but I want you into that auxiliary qubit. But this, at a more state-based level, let's walk you through, well, how do we know here, right? What I just explained with, the initial state. So let's say a 0 state, then the 1 state, and then the 2nd state before the measurement. In this cat, we're going to see the state of all 3, right? So this is going to be an operation between these, and the product of this is going to align the potential states. So 0, 0, 0, 0, 1, 1, and then the probabilities, as I told you here. When we look at the probabilities of this state, we're looking at the and there's a lot of math that goes into it, but what I want you to know is that this is what we're doing is observing the different potential states that could appear there with the combination. And so this first state, and just let's see if we can remember, so 0, 0, 1, 1, 1, 0, and then the other one, right? You want to think about this as what potential state could alpha have and what potential state could beta have, and then look at it in this context over here for the initial state, and then for the 2nd state, we would be looking at, again, the potential combinations here. And so it could collapse to 0, and here are all different products, right? Look at the separation of the qubits, right? So what we're doing is saying, okay, let's look at the states here. And then we're looking at the potential outcomes that are going to come out of this. I'm probably not doing the best explanation, but I want you to be able to follow this. Oh, let me stop this annotator when we look at this. So if we go back to the image and you think about the measurements with probabilities, that's all we're doing, right? And so if the outcome of A and B is 0, 0 with a quarter of the probability, then the state would become this. Now, the first operation over here, it was giving us the possibilities of, well, what are the states, right? That could potentially come here, because that is what we do when we calculate probabilities. And then it takes you through the different potential states and what the probability of each one of them is. And then here you can do a little bit of a deeper dive into the protocol and look at the additional qubits that will not be affected. And so if you wanted to look at the code, I recommend going to this other one over here let me just share that one. Go to the courses over here. Second. So this Qiskit in the classroom is the usual one that is explained historically, the basis of when they even named it quantum teleportation. So here is Dr. Katie McCormick that explains it. And this is from Qiskit in the Classroom for Computer Science. It's another training that you can look at. And it talks about it with just the 2 states, right? It's a little bit more simple to understand. So instead of combination of the 3, you can look at this in this with the Hadamard, post the gate here with the Hadamard gate. And then you can see the examples of, we talked about this ket being, 0, this would be 1, and then you can look at what we reviewed last week, which was the quantum circuit registry, applying the Hadamard gate to 0, which is from right to left. So in Qiskit, if we have 4 qubits, then we're going to say, 0, 1, 2, 3, and then and that's how it's going to be also visualized and represented, so you know when to apply your qubits. What I mean by that is that this would be qubit 0, and the second one from right to left would be qubit 1. You could see what the C0 transformation here is, which I think is better explained than the basics. And then you can see the flip: 0 to 0, 0, 0 to 1, 1. And remember that it's dependent on the state. So why does this flip? It's because it is the control qubit is 0 here. Let me make this bigger, see if we can make it. The control qubit is this one over here. So control is going to be this one on this side. And the target qubit is going to be over here. Now, this target qubit is going to be on this side. What happens here is you see 0, 0, it's going to be 0, 0. If this one's 0, then the other one is going to be 1. If this one's 1, then this one is going to be 0. If this one's 1, it's going to be, and so you can start seeing the combination that comes here. Notice that it does not change, right? And then you can start seeing the C0s based on the different states. Let me see what else I'd like to explain here. You can see the C0 here. Let me clear these annotations. And then here's more equally, more easily explain the X gate, 1 from 0 to 1, 1 to 0. This is what it looks like in a matrix representation. And then you can look at the gates as they are created right down here. So we have the gate that we reviewed earlier in the week. We have the Z gate. And again, I had mentioned to you that the criticality of the Z gate was the phase. What I mean from the phase is that in this amazing sphere over here, this is the Z gate. I'm sorry. My gosh, forget that. Let me annotate here. So we have X. I shouldn't be allowed to do this. Let me clear this and try again. Okay. So we have so Y and X and then the Z's, right? And so what it would be doing would be flipping within the Z to the negative plane or vice versa, right? And so this is what it's doing. And then when we're talking about a C0, or a control flip, is that it would be, if this is state 1, because in the block sphere, let's say it's placed over here, then flipping it would mean taking it this way and placing it over here. Same with Y. If this is the state 1, then it would flip it down to state 0. Okay, so you can download this code and play with it. It is explained here now with the Hadamard gate applied and the different things, and it just takes you through the math and the states. And it's easier when it's 1 to 2 qubits, where the state of one controls the other, right? Not what's in the ket, but the state of it. And then you can look here at the outcomes. And so if this is, remember there's target and control, right? And so 0, 0, Bob's state would be the CNOT, and then the result would be a 0, 1, because it would be then dependent on the states. Now, why is it alpha 0 and alpha 1? Is because the first point in time, then the second point in time, as those measurements progressed, which in the other examples are represented by phi. Here is the code. You can download the notebook here and go through it. This is how it represents the unitary matrix to measure the classical register, which is what I explained to you earlier. And it is important for you to know that here in this section, because this will be on your quiz, when we import from Qiskit, we are defining here the classical register and the quantum register. You can follow it by these different states, but then notice that C is the classical register, which could, and the number it has here, okay? So then it would be C0, C1, C2, and this would be 1 qubit, which would be, let's say, qubit 0, okay? Now we're going to go down here in this code briefly to show you one more thing. Here's the gate. We apply Hadamard to Alice. We apply the CNOT to Alice and Bond. Remember the target and the one that changes. And then here is where we start looking at the what's it called? The interpretation and the transmission, and then the measurement, right? So she can only do it if she gets the unitary range. Notice here that theta, and so this unitary variable is just created random variables for the experiment, and then it's like a random generator in a way, more simplified. And so here you go, and you can see that he uses the same thing and then measures the qubit, and then that's why we get this. It's super important. This is not reality. We do not measure this at the end. This is only and exclusively for this example, so they can make sure that the measurement was correct for when they were developing the quantum hardware. And I'm going to stop there to see if we have questions. And I just want you to remember that communication protocol, basis of encryption, you're not able to observe it because once you measure the state of 1 qubit, it collapses, right? And you can't take that point in the sphere and just immediately apply it. That's why that last unitary matrix might be confusing. But this gets bigger and more complicated. But even if someone is observing, those are the intricacies of how it is. Even though the CNOT or the flip happens in these other planes, that information is kept in the Z phase, in the negative phase itself. As you continue observing bigger algorithms, or you go into things like phase kickback, you can see all of the math that goes into justifying this process of teleportation, and you will be able to better understand why, as you get ahead, you find the oracles and the same patterns. So, Hadamard oracles, you'll have, with the angle rotations, again, there'll be a rotation that will take it to, like the poly rotations that we talked about, the 90 degrees and 180, you'll be able to find trends as what we're trying to do. What are the steps to achieve entanglement, get things in the states, make them interdependent, and observe that if, for example, for drug discovery or the quantum chemistry, as he was explaining, where are we looking at the dependence of this molecule with this molecule, let's say for blood-brain barrier protein impact, and what are the other, so how many qubits would you need? What would be the depth of that circuit for you to be able to have an algorithm that is simple enough that the transpiler or it translates it into the existing quantum circuit in a simple way, and that could translate to savings for your computing time, right? If you're going to use very fancy things that don't map as well to some of this, then you will find yourself with longer running jobs, things that you don't always need. So the basics are super, super important, especially when you're trying, when it's on your dime that you are experimenting, or when cost is a thing, which especially with quantum computing, it definitely is. So, questions? Okay. Concerns. All right. Let me just check the Discord channel, make sure there's nothing there. Okay, sounds good. All right, so in the so two announcements I'm going to make because of the request of several individuals. I am going to extend the deadline for the fundamentals quiz. It seems like the first week some people had issues joining, and we have more people that are coming to our event in this other week. That said, given we have completed 50% of the quantum machine learning, I very highly, strongly recommend that you also go through that module within the IBM platform if this is your objective. If you are going to take the fundamental certification, then definitely look at some of the other information that we are explaining. I'm going to share my screen again to walk you through what this looks like. And not, it's not fundamentals, it's the basics. Where is it? Let's see, single systems. No, it's not coming up. I don't know why, it's giving me an error. So what I'm gonna do is I'm gonna send you the course in the announcements so you can make sure that you are looking into it, and that when you are looking for a different way of information to be explained, that you know exactly how to look at it. And so let me see, Grover's algorithm. Here we go. Okay. Okay. The notebook that we're going to share runs you through this. The Dosh-Josa and algorithm, Simon's algorithm, and I don't think it has Grover's algorithm, but it's going to help you get forward in this. Again, the changes of states, right? That this will walk you through some of the math and the states, and talk to you about the strings in a different way. We have been asking people when, if they have any questions, please make sure that you ask them publicly. We have the mentors and everyone very, very much available for you to better understand this. For some, if you're not technical, this could be very difficult. If this is very easy for you, that's wonderful. But you can see here that it talks a little bit about that unitary function, and it does Again, this all it means is that we're going to look at the state, not look, but we're not going to measure it. This is the measurement that collapses the state, but we're going to say, well, what does it look like before I apply this gate? What does it look like after I apply the unitary function? What is it going to look like, after the Hadamard? And so that is what these mathematical explanations are. And so you'll be able to see these different representations here. And then the notebook that we have just walks you through an example of it. So we are not going to be keeping track of who takes these courses to get the badges. All we are doing is extended Kiss Game Fall Fest and our knowledge to support you in doing so. All right. If there is nothing else and there are no questions, then we are going to wrap it up. To motivate you for the hackathons, we have $2,000 in computing time. We have quantum machine learning books. We have grants to support you in your research, meaning what? That we will help you with your hotel or your airfare. We also have some education grants. You can choose between the two. And the objective with all of this information is to better prepare you to be able to put architectures together to solve real world problems. So in following order, first week, we were like, here's the world around us. How can I translate potatoes into numbers and datas and this whole workflow? Then we looked at, okay, well, in the reality of a world where not everyone's going to have a cylinder of this beautiful chandelier at home, let's look at this quantum machine learning aspects for classical algorithms, quantum algorithms, and then bring them together in quantum machine learning. Then, assuming you can look at the opportunities there, you can say, quantum chemistry, I could do this quantum chemistry or neurology or material science, which Ali will talk to you about next week. You can also use it for the analysis of some of the security problems that we're going to look at. So upcoming next week, PQC, KQD, and the continuation of some amazing examples of applied quantum. So thank you for your time. Have a great weekend, and I will be sending the new date for the quiz, probably going to extend it one more week so you have enough time to go through the notebook. All right. Thanks again. Bye-bye.